Are electric boats safe for us to use in the water? The reality is a high voltage battery pack has inherent dangers. I mean, there's a lot of power, there's high voltage, there's a shock risk, and there are fire risks. These are things that we know. What are the steps, are there steps that battery manufacturers have taken to actually make these things safe for use on the water in a boat? Well, to answer those questions, I'm here at Stafl Systems in San Francisco, California. They're going to take me inside. They're going to show me how they build their packs, everything that goes into it, and all the safety factors that they've used to mitigate all these risks. Come on, let's take a look.
My name is Eric Stafl. I'm the president and founder of Stafl Systems. I'm an MIT graduate with a degree in electrical engineering and computer science. We've been working on high-performance battery systems since 2010. We have done a number of leading electric marine platforms, including electric speedboats, electric e-foil surfboards, and electric jet skis. So we have a lot of experience in the electric marine environment. I'm really excited to talk to you about some of the best practices that we've discovered. So a properly designed battery system for safety has multiple layers of safety infrastructure that protects it in all conditions. So the first thing that you have is a battery management system. A battery management system protects the pack from ever getting overcharged, over discharged, too hot or too cold, and a variety of other conditions that could potentially cause damage to the battery pack and the cells. But you always have to assume that there's a small chance that the BMS for some reason could fail. So in the case that the BMS fails, you also have what's called passive propagation resistance, which means that if a single cell goes into thermal runaway, i.e. creates a fire, for any reason, it is only contained to that cell and it does not cascade into adjacent cells and bring down the entire battery pack. That is ensured via certain thermal and mechanical design elements that make sure that there's no way that one cell can take down the entire pack. The other thing you have to do is think about additional mechanisms at the system level that can keep the pack safe. So typically that has to do with structure. You don't want to have the battery pack kind of floating out in a way that it can get hit by something. You want to have it core to the central of the boat. So if you bump up against the dock or some rock or something, the battery pack's not going to be impacted directly. So there's a number of different layers of safety you have to think about. But if you have a proper layered approach, the probability of a catastrophic failure is extremely low, and batteries designed in a proper way like that can be very safe. All right, so let's give you a tour here of Stafl Systems. Any good engineering office is a fully stocked kitchen to keep everyone happy. Very important. This is our electrical engineering lab. This is where we do our board bring up for our battery management systems, or BMSs, as well as controllers. So what that is a printed circuit board with different components on it that runs software to monitor and maintain the safety of the battery pack. So we do all that development here. We've got a ton of equipment. We've got oscilloscopes, power supplies, function generators, hardware in the loop testers, automatic optical inspection, all sorts of stuff. So this is where the electrical and software magic happens. But let me show you the workshop. All right. So this is where we do our battery pack assembly and fabrication of components. So this is our 3D printing center. We have 4 3D printing technologies here, including 2 top-of-the-line MJF 3D printers from HP. So we have HP 5200 and HP 580. These are 3D printers that can do structural grade nylon PA12. The great thing about having this capability in-house is that we have a call for parts at about 3 o'clock every day, and then the engineers release their designs. We do a print overnight, we process it the next morning, and it's on their desk at noon the next day. So we're very focused on quick turn iteration, trying to make the prototyping process almost as fast as software development. These are some representative models of different battery modules we have. So this particular design shows a small format pouch cell arranged in I think a 8S 8P configuration. It shows the multi-layers of separators between the individual cell stacks. So you've got a foam layer, a mica layer, and a graphite layer for thermal conductivity. These help our engineers understand what the design they're putting together in CAD is. Some of the phenomenal things about this 3D printer, especially the 580, is you can print full 3D models in one go. So this was all printed overnight in one quick process. This shows a high-performance, large format pouch cell module that uses opposing cell tabs, because this is actually a very high energy density and high-performance module for large energy storage systems. Over here, we have some prints for cylindrical packs. This is actually using a nylon PA12 from the MJF 5200, and this allows us to get excellent dimensional accuracy and produce up to hundreds of units, so we can do low volume production with this 3D printed material. Finally, one of my favorite machines here is actually this SLS from Form Labs. another company founded by MIT alums. This amazing technology is so accurate that it can print threads like this that just feel just like a normal screw. So it's just incredible.
That's really incredible.
And this technology didn't exist 5, 6, 7 years ago. So this capability is only available today. So this here is the print bed. So basically what happens is you go in and you have a powder, and that powder goes through various thin layers, and it actually melts that powder to create these shapes. So what's kind of neat is you have this rectangular volume, and every night we package all the different parts that need to be printed, and then put that together in one print volume, and then print the whole batch, and then process them with our bead blasting system, where we basically can clean out all the powder here, and then we bead blast it here, so that by the time the part comes out, it's nice and clean. It doesn't have any residual things. Here's a view of actually a printer in action. So you can see the layers. Basically, it's putting down a very fine layer of this powder material, and it's printing this using this very precise heater. And so layer by layer, it slowly builds up the part. The other thing that's really cool is we reclaim about 80 to 90% of the material here. So all the unused print volume, we actually get to reuse that powder and can put it back into the next print. So it's a very efficient process, very low cost, but having the capability in-house allows us to go quickly. Over here, this is our laser welding center. So we have a IPG 1000-watt fiber laser. And this system allows us to actually do the cell interconnect between different cells. So whether it's a pouch cell or cylindrical cell, we use laser welding to connect a bus bar or collector plate to the top of the cell terminal, such that we can electrically interconnect the cells in a very high reliability way. The great thing about laser welding is it's very, very accurate, it's very fast, and you can control very precisely how much energy is being delivered. So you can come up with very sophisticated weld patterns that have a lot of surface area and are very mechanically and electrically robust. We test that with pull testers. So we have 2 different pull testers here, so we can basically assess the mechanical strength of different welds. We also have a cross-sectional analysis laboratory where we can cut a weld and see exactly how much penetration we have of the laser, such that we don't over-penetrate or under-penetrate the weld, and we have the proper depth of weld for our application. Over here, we have some laser welded cold plates. So this is a cold plate technology we've developed in-house. Basically, what we've done is create a stack up of different materials, of different layers of aluminum that all get laser welded and then bonded together. And this creates a cold plate channel that coolant comes in one side, distributes and turbulates throughout the cold channel, and then comes out the other side. And that way we can keep our batteries cool or warm and at the ideal temperature for operation.
Why is it important to be so precise in your depth of weld?
So being precise in the depth of weld is very important, particularly for a cylindrical cell, because a cylindrical cell has a relatively thin can wall. If you create a really thin weld, then it's not going to be as mechanically robust as you want it to be. So in shock and vibration, it could pop off. But if you create a weld that's too deep, you're actually going to create a crack in the cell can, and you're going to get a leaking of electrolyte, and that can create some damage, and the cell will not perform normally.
Are these cooling plates, would you run glycol through those? Or?
Yes, it would be a 50-50 water glycol, typically. Oh. Although you could use pure water, kind of any water-based system with antifreeze.
Is that what you guys have found has been the best cooling as far as water
the
glycol?
industry standard is 50-50 water glycol. Yeah. In terms of weld depth, we find that with cylindrical cells, you typically have about 300 microns of cell can thickness, and we've determined that the proper ratio is 1/3 of the cell can thickness to have the proper balance of strength, but also not over-penetrating and weakening and creating a crack that could later cause a leak. So basically, out of 300 microns of can thickness, you're looking at trying to get a penetration of 100 microns through about 200 to 250 microns of nickel-plated copper, such that you get the perfect weld that has a good long-term reliability and electrical performance. Over here, we have a 5-axis CNC. So this is where we can do quick turn cuts of different parts or jigs. So for example, let me show you here. This is a part that we prototyped in-house using this 5-axis CNC. The great thing about having this capability in-house is our engineers can release a part, and our full-time machinist, Skip, can give them feedback right away about, for example, some of the geometries, some of the hole sizes, some of the different cuts, such that the part is more manufacturable and can be done on a faster process in the CNC. So that feedback loop is super valuable for the learning cycle for our engineers.
These are all your bits for the
yes,
CNC
exactly.
machine?
So our CNC has a number of different bits. It has a tool changer, so you can automatically load up different tools and run the program and cut multiple parts sometimes at the same time.
Right on.
And then over here, these are our laser cutters. So we have a 4,000 watt fiber laser cutter for conductive material. This is great for cutting metals between really thick and really thin metals. The thing that's really amazing about this laser cutter is we can cut up to 1/4 inch steel with this laser cutter, or we can go down and cut very thin sheets of nickel clad copper for our collector plates. So for example, the same piece of equipment can cut this steel or can cut these fine geometries. This is 200 micron thick nickel plated copper. And this is what we're actually using to weld, in this instance, to cylindrical cells.
That is so cool. Or this big heavy steel plate. That's
exactly all on the same equipment. And you know, 1 minute you could be running a cut here, another minute you could be running a cut here. It's just software settings. Wow. And I think this machine has set the record for the fastest turnaround we've ever had on a part. It's been 20 minutes since the release of an engineer to the part on their desk. So we can move very, very quickly with this. Over here, this is our 150 watt CO2 laser. So this allows us to cut non-conductive materials, so mica, some plastics, some foams, that sort of thing. And basically this allows us to have very fine geometries and scoring for different non-metallic components. So mica, this material I'm holding here, is very important for battery packs because mica is a very high temperature capable material. So you can actually take a blowtorch with mica. If it was a solid piece, I could take a blowtorch, push it on my hand, and I wouldn't feel heat on the other side.
Really?
So this material is very good for cell-to-cell anti-propagation.
Using it to thermally insulate between cells.
That's exactly right. Yeah. So mica you can use to thermally insulate either between cells or also at the top of the pack or bottom of the pack to make sure that flame does not escape through either a plastic or metal enclosure. Because one of the things about lithium-ion batteries is that the thermal runaway temperature can actually exceed the melting temperature of aluminum. But generally speaking, you want to use aluminum if you can because it's lighter than steel. So using mica in combination with aluminum or aerogel or even more sophisticated materials for a similar purpose can be really effective to control the thermal path in a runaway scenario.
Is this a high cost material?
No, very low cost.
Really?
Yep.
It's actually a naturally occurring material too.
Yep. Mica has actually been used for thousands of years for various things, but now we get to use it for this this capability.
Is it a mineral?
Yeah, it's actually it's a mineral kind of. It's got this rock grainy structure to it. So it's like a component that you'd find in certain certain mineral deposits. Yeah. And then over here we have a number of different programs going on. We're actually simulating a very large battery system here. Obviously, it's a work in progress. This is going to take a number of BMS boards connected in a series arrangement to simulate an extremely large battery system for a very large vehicle. So these are some PDUs or power distribution units that we're building up for one of our high voltage battery packs that we're actually using in an electric jet ski application. So this is a power distribution unit, or PDU as we call it. It has two main disconnect switches on the positive and negative terminal. It has a pre-charge circuit, a current sensor, a fuse, and then the BMS system. So basically what this does is it contains the brains and the safety functions to disconnect the battery pack from the external world. So one of the things we think is very important for battery pack safety is that all the voltage and power is contained within the battery until the BMS communicates with the external system and passes all its safety checks. Then it closes these switches so that you have power available at the external terminals. Otherwise, it's completely safe and touch safe.
These are the switches?
Yes.
Okay.
Those are basically huge relays. Yeah.
And then the relay will close once to send
Correct.
power.
That's exactly
once it gets
right.
a signal from the BMS.
That's exactly right. Yep. Over here we have what we call our high pot system or high potential testing. So we can to test the isolation, electrical isolation between your high voltage domain and low voltage domain. One of the things for shock safety that's very important is that the battery cells themselves are electrically insulated from the case. So you never want to have your negative terminal or positive terminal or any interstitial terminals electrically connected to the case for shock safety. So one of the ways you check that is to make sure you have excellent isolation resistance and high potential withstand voltage between your high voltage domain and low voltage domain. So what we do is we basically, in a test, we apply 5,000 volts or up to 12,000 volts between the center of the battery pack, the electrical connections, and the outside of the battery pack, and ensure that all our electrical insulating layers are functioning as expected. And there's a huge amount of overage on that because our battery packs are typically 400 volts or 800 volts, and if we're testing at 5 kilovolts, that's about 6 times higher voltage than it needs to be, but you need to do that for the capability of the isolation barrier. So the isolation barrier is something that you want to monitor over the health of the battery as well. So we actually have some patented technology that does that for us. It's called vectored isolation monitoring. And what that does is it basically measures the resistance between your high voltage domain and your low voltage domain. And it tells you not only what the magnitude of your resistance, the resistance of the isolation fault is, but where in the electrical stack it is, and also what the Y capacitance contribution is. So that allows you to assess what the total available shock risk is. And what happens over time is if that resistance starts going down, then you can tell that you're having a breakdown of your isolation, and then you'd want to take the pack offline such that it doesn't create a shock hazard to the user. At a high level, a battery pack consists primarily of a stack of lithium-ion cells. So typically for an electric marine application, you're talking about a 400 volt or an 800 volt battery system. That would be comprised of typically 96 cells in series or 192 cells in series. Those are all electrically connected with copper. Then what you do is you put that in an enclosure that's fully sealed to make sure that obviously none of the seawater or environment gets into the pack. But you also have to combine that with sophisticated electronics and software to monitor the safety of the system. So specifically, you're looking to make sure that the cells in the pack never get too hot, never get too cold, never get overcharged or over discharged, because you have this operational window where you want to keep the cells in so that the electrochemistry is safe. If you do that properly, then essentially you have a reserve power system that can be charged and discharged at will. So basically you're discharging during operation, with the motor, and you come into shore at the dock and you do a charge, either overnight with the AC system or, very quickly with the DC fast charge system. So basically it fully replaces the fuel tank and is the energy storage device for the boat. Over here we have some battery packs in the different states of assembly. So we're actually putting together these high voltage battery packs. This is what it looks like when the battery pack is completed. This is the face that has all the connections to the rest of the system. So for example, this is a coolant inlet. So cold coolant would come in here. It would distribute within the pack through these cold plates and then cool the cells so they don't get too hot during operation or charge. And then you pull out the warmer coolant here and put it through a radiator and a pump. Here, this is a high voltage connector. This is a shielded high voltage connector with something called HVIL, or high voltage interlock. What that allows you to do is it detects if the connector is present. So that way, if for any reason the connector becomes disconnected, there's no way for the system to close contactors such that there's no voltage ever exposed at these terminals if it's disconnected. This is the low voltage power and communication interface to the rest of the system. So typically 12 volts is coming in here and it's communicating via something like CAN bus or Ethernet to the rest of the system, and it has some discrete I/O as well. And that allows you to handshake with the vehicle controller or the vessel controller and then turn on the battery pack and make sure that everything is safe to go before you connect power. Finally, we have some lights here just for operator knowledge about how the battery pack's performing. So then this is what it looks like internally. Obviously, this battery pack is a state of partial assembly, but this shows different modules connected in electrical series connection such that we build up the voltage and thus power of the system that we're trying to power. So this is a 400 volt battery pack that's actually being used in a jet ski application.
How important is cooling for a battery pack?
So cooling is very important, especially for high power applications. So in the marine environment, high power is kind of the name of the game because you have a lot of water you're pushing out of the way. And so you want to make sure that your battery pack doesn't overheat so that you don't have to reduce your current draw just to help it cool down. So by having great cooling management, you can keep your battery pack in the ideal temperature and operate it as long as the state of charge will allow. Okay. One thing that's actually really nice about the marine environment is you have an infinite thermal reservoir with the water. So basically, you can have a heat exchanger with either lake or seawater that then exchanges it with a coolant such that you get between 15 degrees C and 30 degrees C water, and then you can basically evacuate as much heat as you want out of that.
Do you guys see a difference between, let's say, an automotive battery and a marine battery as far as the power discharge?
That's a great question. So yes, because a marine battery, generally speaking, when you're up to speed, you're pulling pretty much full power because you're pushing a lot of water. So you're pulling a lot more power than on an electric vehicle, because electric vehicle, you basically are pulling a lot of power when you're accelerating, but when you're cruising, your power level is not as high. So electric vehicle batteries actually are not that power dense. They're mainly energy packs. But for marine, especially high performance marine, you do have some power demands on it that are in excess of what would typically be seen in an electric vehicle pack. That being said, if you have a very, very large marine pack, then the power level comes down, relatively speaking. So it kind of depends on the vessel and what the power level of the vessel is. over here, this is actually a pretty interesting project we were working on. We were doing a powertrain simulator for a high-performance electric boat with DC fast charge. So this is actually using a DC fast charge plug, and then we were simulating the controls and contactors and system such that we could test it out with a CCS fast charger. So basically, you'd have a CCS fast charger on the dock, plug it in, you could charge your boat, and then sail away when it's done. So this here is our SMT work cell. So we can do PCBA assembly here. So this is where we basically take bare circuit boards that we get from one of our vendors, and then we populate the individual components onto those circuit boards such that we can actually take those boards to the electrical engineering lab, fire them up, get this, the circuitry tested and working. So this is called a pick and place machine for surface mount technology. Basically, it has all these little tiny parts on these reels, and the robot goes through and it uses a optical computer vision system to pick up each component and place it precisely on the board. And then we take that and then we put that in a reflow oven such that the solder melts and all the components on the board get connected electrically and mechanically to the system. So you can see that this robot is firing up right now. All right, over here is our high voltage test area and cell testing area. So we have a number of environmental chambers that we test the battery cells at different temperatures and humidity levels, and then we can run it at different charge and discharge rates. So one of the things that's very important for us is developing what we call state of charge and state of health accuracy algorithms. And what that allows us to do is estimate the state of charge of a battery pack, which is basically the fuel gauge, how much energy you have remaining, and state of health, because one of the things that's interesting about battery packs is over time, the amount of energy they can store typically goes down. So, a fresh battery pack can store 100% of the energy at the beginning of life, and then maybe after 1,000 cycles, you're down to 90% beginning of life capacity. So we need to estimate that very accurately so that a user always is very confident that when the battery pack fuel gauge says you have 40% remaining, you truly have 40% remaining. And it's not like one of those phone things where, it says 20% and then 1 minute later it's the phone shutting off. Unfortunately, we all have that experience. It's because of bad SOC estimation. So we put a lot of time into that here. We use a Kalman filtered approach, which is very good. This is a chroma cell simulator. This allows us to have 32 different channels of charging and discharging cells very precisely so we can measure exactly how the cell is performing. One of the things we found that's very important is that we trust but verify our cell vendors, because we find that cell vendor data is not always apples to apples comparable. So we generate all our own data sets, all our own data sheets for these cells, so we can see exactly how each cell chemistry and type performs in the real world. And that's what we do with this equipment here.
What do you find that humidity does to a cell over time?
Yeah, that's a great question. So humidity is really more, we actually typically use humidity testing more for like module level testing, because humidity, we want to make sure that when the humidity cycling is going up and down, you can get condensation. And we basically test that we have a good conformal coating layer and application such that we don't have any undesired conductivity between adjacent conductors that is caused by the humidity. So the humidity itself typically doesn't affect the performance of the cell directly, but it affects the performance of the overall module in terms of long-term safety.
So in different temperature environments, you might get some moisture in the pack.
Exactly.
It's probably inevitable.
Yeah, so you're going to get moisture in the pack because you need to have a Gore breather, and the Gore breather doesn't allow liquid water to go through, but allows water vapor to go through. Mm-hmm. And so one of the ways we solve that is with a desiccant package within the pack that helps absorb a bunch of that moisture and keeps the humidity levels within the pack lower, such that the probability of condensation is much less. And even if there is condensation, we use a lot of potting and conformal coating and other coverage methods to prevent the condensation from ever affecting the safety of the battery pack. Here, this is a motor dynamometer. It's partially assembled right now. We use this to basically assess the performance and efficiency and operation of a motor and inverter pair at different RPMs and different voltages and different operating conditions. This allows us to measure very accurately the speed of the rotation as well as the torque being applied between the motor and then a load motor or generator in this case. Yeah, so this Hall effect torque transducer sensor is extremely accurate. We get very, very precise torque measurements at 16 kilohertz. So basically, I think it's plus minus 1% of accuracy at 16 kilohertz. So we can actually see the torque ripple, you know, because no motor generates perfectly even torque throughout the rotational window. So you see a little bit of what's called torque ripple, which is like a little bit, like sometimes it's pushing a little harder, sometimes pushing less. And we can see how that torque ripple changes in different operating conditions. So a properly designed motor and inverter pair really minimizes that torque ripple such that it's quieter and smoother and more efficient in general. So over here, we're doing some ESD testing. This is basically electrostatic discharge. We're basically taking an ESD gun. You can see what this is. This generates a lot of static electricity to the same way that, you know, walking across a dry carpet would.
So don't touch the end of it.
So don't touch the end, especially when it's powered. But it can generate sparks about that big. And so we zap the boards to make sure that, and the electronics, that they work even in an environment where sometimes you get electrostatic discharge. This is a battery module under test. You know, basically seeing how it performs thermally. We use a variety of different cyclers here. We have a module level cycler that's grid interactive, which means it charges and discharges actively to the grid. And then we have a 1,000 volt, 60 kilowatt bidirectional supply, so we can charge and discharge from the grid up to 1,000 volts with this piece of equipment.
How many cycles will you run the battery through?
Great question. It depends on what we're doing. In this case, we're looking at thermal characterization, so we're going to be probably running about 6 to 12 different tests at different charge and discharge rates. But then for cycle life testing, we would do, you know, more like 1,000 cycles or 2,000 cycles. So charge it up and down a bunch of times. Yep. This is a coolant preconditioner. So what this does is it allows us to set a coolant temperature and coolant flow rate, so we can simulate our liquid cooled batteries and cold plates to see how they actually would perform in a liquid cooling scenario. Yes, so liquid cooled batteries perform a lot better than non-liquid cooled batteries because liquid cooling allows you to really get that heat out. So for example, a battery pack that is not liquid cooled, you might be able to discharge it what's called a 1C rate, which means you can discharge it at, you know, the full pack in an hour. But a pack with liquid cooling could let you get as high as a 5C rate or a 4C rate, which means that you're discharging the entire pack in about, you know, 12 or 15 minutes. Yeah, and then over here, we actually have a full UN383 test lab. So what does that mean? Battery packs, in order to be able to ship them, particularly by air, you have to test them to make sure they're safe in abuse conditions. So UN383 is an international standard for shipping battery packs, you know, via air. So we have what's called T1 through T7 here. Those are the different tests you perform. T1 is an altitude test. So basically we simulate the battery packs at 60,000 feet equivalent altitude to simulate
this is basically like a vacuum chamber.
This is a vacuum chamber, exactly. So we can simulate basically what happens when you know, a battery's on an aircraft that goes decompression. So that's what this is simulating. This is a shock tester. So what we do is we basically take a battery module and we put it on here and we drop it from different heights onto different discs that basically create a different half-sine pulse that essentially shocks the battery. We usually do it in different orientations to simulate drops and shocks and that sort of thing. So this is very important for the marine industry because every time the boat is hitting a wave, we want to make sure that the battery pack is not going to get damaged by that. So we typically test up to 50 to 150 Gs of shock. Typically it's like a 6 millisecond sine wave pulse. Here, this is a vibration tester. So what this does is allows us to take a battery module or board or unit, kind of anything we can test, and we can run a frequency sweep. So basically we can set different Gs we want to test at different frequencies to see if there's any resonant patterns or vibratory modes where something could get damaged. So for example, what we're looking at here is you can actually have, this is a transient test, so you can actually see the vibration and the acceleration at different times, but we can also run frequency sweeps where basically you start out at 20 hertz, go to 1000 hertz, and run different G magnitudes of amplitude to test that out. One thing that's funny about this is sometimes when you get a certain frequency that resonates with the building, the whole building starts to shake.
Like a musical instrument or something.
Exactly, yeah,
Amazing.
yeah.
So based on your testing, the shock testing and the vibration, what have you had to do to the pack structure to, I guess, mitigate those?
Yeah, there's a lot of learning from that. It's one of the things you can't just simulate. You really have to test and learn from. So it's really helped us to come up with good ways of capturing cells so that you never want to have a cell that's kind of loose within a battery pack because then it can kind of jiggle around and get damaged. So we think about foams, we think about potting, we think about RTVs, different kind of compliant mediums that allow you to capture the cell with some flexibility such that the shock and vibration don't create actual damage to like a collector plate or a cell tab or something like that.
Yeah, it's so important, especially in a marine environment on a fast boat where you're just getting so many impacts.
Exactly. Yeah. So that's very important. We find that testing is critical, especially for the marine environment. And then over here, this is a CNC conformal coating machine. So basically what we do is we can apply a clear coat conformal coating to all our boards such that they will perform better in humid or contaminated conditions. So this is very important for marine because it helps prevent contamination, increases device lifetime. So the marine environment, I just want to be very clear, is a challenging environment for high-performance lithium-ion batteries, primarily because of, in the ocean, you have seawater. Seawater is highly conductive, highly corrosive, and so that is typically very difficult to manage with electronics. So that's where sealing comes in. So with any properly designed lithium-ion battery pack, you have to have an excellent enclosure, an excellent seal, such that you have no ingress of moisture or water, because that can cause a major problem. So there's two things you do for that. You have to have excellent sealing technology. You have to have what's called a breather vent, because what happens is you have to make sure that as pressure and temperature change over time, the pack enclosure does not effectively act like a balloon and build a differential pressure. Because if you ever build differential pressure, it's easier for fluid or moisture to go one way or the other. The other thing you need to do is have detectability. So every seal, even if it's perfectly designed, will eventually have failure points. So the thing you want to do is have different sensors within the battery pack that can tell you if there's abnormal levels of humidity, if there's corrosion going on, or if there's submersion of water. Because oftentimes there are, there's a long period of time typically between a detection of some sort of risk and an actual event. So the key would be if you detect you have corrosion or water or humidity that is beyond what's expected within the pack, you would prevent that pack from charging again. Because the best thing you can do for a battery pack that has some sort of issues is discharge it, because a discharged battery pack has a lot less energy content than a fully charged battery pack, and therefore it's safer from a thermal runaway perspective. All right, so this is where we store our cells and modules that are in various processes of assembly. So there's a number of different cell form factors that are pretty common in the industry. Cylindrical, which is something that you may have heard of before. This is a 2170. There's also 18650s and other cylindrical form factors that are pretty common. This is being used by Tesla, for example, for their battery pack. This is a prismatic cell. What prismatic means basically it's contained in its own hard case, and it's got terminals right there. So these are easier to package in some ways and have other characteristics. This is a pouch cell. This is a unidirectional pouch cell, which means that you have the tabs all on one side, so basically positive and negative, and then current flows in loops. This is also another pouch cell. It's called a bidirectional pouch cell, which means that the cell tabs are on opposite sides. Now, we find that a cell in this form factor is actually more ideal because you have uniform current flow across the entire cell face or body, which means that your thermal distribution throughout the cell is more even, which means the cell actually lasts longer and has higher performance. So, each cell has its own pros and cons. Sometimes it's literally about which cell fits in the space available, but cell form factor is one of the important considerations to think about when you're designing a pack.
Can you just talk maybe a little bit more about, so why would you use a prismatic over pouch cell?
Yeah, good question. So prismatic cells are good for really just ease of packaging. So the thing that's nice about prismatic is you don't really need to worry too much about the expansion to the same degree as a pouch cell. They're rigid, so it's easier to put in. You don't have to put as much foam and other compliant material in. So that's a pro. The con is that it's typically less energy dense and less power dense. So these are more difficult to package, but if you do it right, can yield higher performance. This is easier to package, but a little less performance. Also, different chemistries sometimes are available in different form factors. Sometimes it's just literally about which cell is actually being made in volume. This happens to be an LTO cell, so in this specific instance, it might make sense because you're looking for LTO. So it's really an availability game about what is the right form factor, what's the right chemistry, what's the right availability. You have to kind of think about all those factors, and then that allows you to make the right cell selection for the project.
Which one would you say is the best for marine applications?
I would say, all things being equal, I would expect that pouch cells or to some degree prismatic cells would be ideal for marine applications. Cylindrical cells, the concern I have about cylindrical cells is that it's a variety of very small, it's a very To make a large pack, you have to have a lot of these in series and parallel, which means you have a lot of these little individual connections. And the problem with little individual connections is they're relatively mechanically weak, and it's just a lot of failure points. So the nice thing about having a much larger pouch cell is, for example, that cell is about a 4.5 amp hour cell. This cell is a 73 amp hour cell. So what's beneficial about this cell is that you have basically 1/20th of the amount of connections to have the same amount of energy approximately. So it's just, you have much less failure points, you have a nice big fat tab to weld to, so you can have a really high confidence mechanical and electrical connection. So generally speaking, for marine, I would expect that we'll see more and more pouch cell packs. That's kind of the ideal solution there.
Speaking about cells, one of the main problems with marine batteries is that the energy density right now is really too low to compete with their gas counterparts. One of the things that Stafl Systems is doing is working with a company called Amprius that makes next generation cells with incredibly high energy density, which can bring the weight of a battery pack way down.
My name is Katie Mays. I'm with Amprius Technologies. We're an advanced battery company based out of Northern California. So what Amprius is doing is we're really effectively a paradigm shift in what we thought was possible with battery technology. So we have extremely high energy density with high power performance too. How we do that is through silicon. So our anode is silicon based. We have 100% pure silicon or high content silicon. And so why we would use silicon over just conventional graphite, it has 10x the specific capacity of graphite. So you're getting a lot more energy per unit of weight. And typically, if you look at a graphite-based cell and what's on the market right now, there's a huge chasm between high energy and high power. So you're really faced with this trade-off decision where you can't have both. You can either have high energy, which is still not very high energy, or you can have even less energy with some power performance. Silicon, what's unique about that is that it takes that big trade-off that exists with graphite and it shortens it significantly. So we're getting extremely high energy density, up to 500 watt hours per kilogram, so super high. We have high power cells that are 10C continuous and 400 watt hours per kilogram. So that's performance that really I don't think industry thought was possible 5 years ago or even 10 years ago. So this is something that you can actively get now. We're not talking about performance that we're going to get in 5-10 years in future tech. This is current tech. And our future tech will be even better than what it is now.
Amprius cells have incredibly high energy density at around 400 to 500 watt hours per kilogram. Now at the pack level, that's different because they have to put in casing and heavy parts to make it safe for use. So the industry standard is about 130 to 150 watt hours per kilogram. Using Amprius cells, they can achieve nearly double that at 280 watt hours per kilogram. But back to safety. Since this industry is so new, are we seeing a lot of government regulation?
There's not a lot of government regulation driving safety in the lithium-ion battery packs, but there are a lot of industry best standards and practices that are being deployed. So for example, UL and ISO have a number of standards that describe how you're supposed to test the pack, how you're supposed to validate that the pack can handle abuse conditions without going into thermal runaway or causing a fire. So for example, UL 2580 is a electric vehicle standard that came out a few years ago that's becoming more and more popular. There's some ISO standards as well. So we're seeing a lot of industry standards that are now becoming required by a lot of customers and OEMs. Good question. I think they cover most of the needs to create a well-engineered pack, but I think there are some corner cases that are specifically relevant for marine that will need to be evolved over time in terms of corrosion, in terms of additional safety features, in terms of something called isolation monitoring. I would expect that over time we'll see more and more of specifications around that.
Well, that's it for this video. A big thank you to the team at Stafl Systems for letting us inside and teaching us all about how they make their amazing battery packs. I hope you learned as much as I did. Thanks for watching.